The idea for the proof is that we should be able to answer all of these queries. And the queries always have the form 1 over S over plus the secret. So the way that this proof actually works is that we're going to use all of these powers. We're going to set up the public key as being of the form, for instance, G to the alpha plus 1, G to the alpha plus 2, G to the alpha plus 1, alpha plus 2, and so on. All of the exponents except the value that contains the challenge input. So the alpha plus the X star will be missing from the public key. And so that's more or less what this proof is doing. And the idea is that once you have to answer a query, we're going to compute simply this public key divided by S plus or alpha plus some input value. And since we have all of the exponents except the challenge input, then we can compute this value without actually doing any division in the exponent. And actually we can generate the public key by using the values that were given to us. So the way that it works is first simplicity, you do a shift, you define beta as alpha minus X star, and because of this, the way we define it, we can very easily compute G to the beta and B, all these elements from the original elements that we received. And then the way we define implicitly this function fz, which is the product of z plus w, where w contains all the elements except for the challenge. So because here all the values, the input values are actually in ZQ. So this polynomial will have degree Q minus 1. So we can very easily, because of that, we can define a G tilde or hat, I think I used hat here, as G to the F of beta. And we actually can compute this value because we know the coefficients. And we actually can use our knowledge of this of G to the beta, all the power of beta. And then we set the public key as actually G hat to the beta. So this means that the secret key is beta, but which we don't know in this construction. So to answer queries, we actually given xi, we define a polynomial fi, which is f of z divided by z plus xi. So because of that, the proof for this value x should be g raised to this fi of beta, because the secret key is beta, which will have this form. And we can answer this query because we know how to compute all the values di. Then to compute v, we simply compute e of g hat, and the proof. And this will actually be a correct value because this is how the check to check actually this value here. That this value is correct. This is going to be exactly the check that is done by the verification algorithm. And to check that this is correct is just by construction. We actually define it properly. We computed the right value. So the part that is actually complicated are actually probably, will the slides be available? Because this part is actually not in the slides there. So if you're looking for it. I said that on Tuesday, so I guess you got the version that got printed didn't contain this part of proof, but the slides will be available. So you can actually check these details, but the idea is actually that if we're going to compute this value here, tau star, that has such a form, which is quite complicated actually. Like I didn't define here the range, but it's not. Some of them go to Q and others go to Q minus 1. But the value f tau 0, actually the important thing is that it has this form, and then we received actually the assumption of word as t, but t is actually got replaced here by tau, which is EGG 1 over alpha. And you can see that if that happens, then if the input that we receive from our decision oracle, or the hardness assumption that we're trying to break, if the value is actually equals to EGG 1 over alpha, then this value here will have this form. And then that is just means that the output of the function will look like pseudorandom, or sorry, will be the correct one. And if the value that we receive from the assumption is actually random, then the value that we give to the challenger is random. So by using the answer from the challenger, we can actually distinguish from if we receive the random input and random value or not. So the probabilities between, this is just way to map the decision problem that I was given to the decision problem that the adversary is expecting. Implicitly it is. Here I never assume that I guessed X star incorrectly, because whenever I guess incorrectly, I will just abort. And because of that, I will lose the factor 1 over the domain. So this only works for small domains. And for small domains, selective security and full security are the same. So, but I think it's easier to think of this as selective secure. But still, it's interesting to see that even if we not only lose a factor 1 over Q on the 1 over the domain size in the reduction, but this reduction, the running time is also proportional to to Q. So it's not only that even if we got even selective security, we can only prove it for small domains, because this part here of the reduction, when we generate the public key, actually takes time that is proportional to Q. So now, like, these are the direct constructions of VRM. So what we notice is that for those of you who are familiar with some of the schemes in the literature, there is a similarity between this VRF scheme and an IBE scheme that it's by Sakai Kasahara. Sorry for not pronouncing the right way. That is actually the following. We can imagine, in that scheme, like in the Sakai Kasahara, if we consider X as being an identity, we will see later the relation more precisely. But if we consider X as being an identity, power of X is exactly the decryption key that you have in the Sakai Kasahara scheme. So this the verification, the proof here is actually has a bit the comparison is not the same. But we can think of it as actually being the decryption under the decryption under this key, or like giving out the proof for a given the secret key for an identity. And if we decrypt a given ciphertext, even if the ciphertext is not for that identity, that is one of the properties that we're going to define for IBE schemes, that is, we call pseudo-random decapsulation. That actually once you expect IBE schemes to satisfy that property, meaning once you decrypt a ciphertext that was not intended to you, that usually the plain text that you get should look random. So this notion, the notion that we're going to need from the IBE is actually something like that. Because it's not a standard notion. Maybe if you have use a CCA scheme, the decryption will simply fail if the ciphertext was not intended to you. But this is not necessarily true for any CCA scheme. So, but we're going to use that property. So based on this idea, we're actually like looking at the similarity. We try to make this connection a bit more formal. And the idea is that we're going to give an IBE-based VRF construction. So how does it work? So here is just like recalling the notion of IBE. So since it has been talked about quite often now, you can skip. But actually for our transformation, it's easier to talk not about IBE schemes, but it's easier to talk about CAMs, or key encapsulation mechanisms. And the difference between an IBE and a CAM, other than you can see that they're almost none, just changed a couple of names. But one of the main ideas that instead of receiving a message here, now given the identity and the public key, the encapsulation mechanism will generate a ciphertext together with the key. And this key can be used to, like by a symmetric encryption algorithm, to actually encrypt the actual message. And the ciphertext gets sent over the network. The receiver, given the ciphertext and the secret key for a particular identity, then you can recover that key. So the standard secure definition for these schemes is the NCP, the equivalent of the NCP scheme for standard public encryption, in which it usually should be hard for you to, for a given challenge identity, it should be hard for you to distinguish between if you receive a ciphertext and the key that was encapsulated, or if you received a random key, you should not be able to tell which key you actually received. So it's standard to the similar to the definition of NCP for standard IBE schemes. And as in the usual notion, you actually can query the oracle, like for identity, you can obtain a secret key for identities other than the challenge. And the idea is that you should not be able to tell which key you received, the real key or just a random one. So, but unfortunately, in order to get this transformation, the property that we need is not quite the right one. It's not quite the standard notion. It's what is actually what we call pseudo-random decapsulation. And the idea is that, imagine for instance, we choose an arbitrary identity, ID 0, and then we encrypt to this identity. Now the adversary will choose some identity, some challenge identity ID star, can be ID 0, in which case if it is ID 0, this secure definition will be equivalent to the standard definition of NCPA, but more generally can be something else. And the idea is that the adversary should not be able to tell apart the decapsulation of K and the decapsulation of C star with respect to identity I star from a random string. So it just means that exactly that. So if I decrypt a ciphertext, even if it was not intended to me, and and I encrypt that ciphertext, that the value that I get should look random. And this should hold even if I get encryption keys for identities other than ID star. I can get, for instance, the secret key for ID 0, as long as ID 0 is different from ID star. So this is just the same definition using pictures, but and then based on these definitions, actually, we can build what we call VRF suitable IBE. So if and essentially the definition says that if the IBE satisfies this property, which we call pseudo-random decapsulation, and that is the part that is hard. Property that calls unique key derivation. Essentially, you can make a weaker assumption, but it's easy to understand, consider this assumption which we call unique key derivation, which essentially says that the key derivation should work like a unique signature scheme, which is a quite strong assumption. And actually, this assumption, called pseudo-random decapsulation, you can see very easily that is satisfied by most CPA IB cameras. So most of the encryption schemes in the literature actually do meet this notion, as long as there's the CPA version. And I say CPA because usually in CCA, once you decrypt with the wrong key, usually it just returns bottom, or like it says invalid. And so the construction itself is quite simple. As we said, we're going to generate an encryption with respect to this ID 0, some arbitrary identity. We're going to generate some C0, K0, we ignore K0, and we publish the public key of the IBCAM scheme plus this ciphertext, C0. Now, the function, the F function is actually this part here, which is like we define pi of x as being the key derivation for input x, where x is the identity. So the input x here of the VRF becomes the identity in the construction. And this actually becomes the proof, and the output of the function becomes the decryption of C0 with respect to this key. So to verify, we actually check that this decrypts correctly, and we check the validity of pi of x, meaning that this is actually a unique signature with respect to x. So,
excuse me. So pi x is ID?
Yeah, because it is the ID in the ID scheme.
And the pi x, the secret key corresponding to ID?
Exactly. So it's exactly what we saw. Like if we, later when we see the Sakai-Kasahara and we instantiate Sakai-Kasahara scheme, with this transformation we get almost exactly Doddy's and Polsky. Not exactly, because like the ciphertext in the Doddy's and Polsky, the ciphertext has a particular, like it was chosen for a particular value of R, random. So that's why the proof of Doddy's and Polsky doesn't follow from our proof, because it assumes a particular random value used in the encryption. But if you don't care about this minor if you, in terms of efficiency, you get the same in hours from this generic construction.
Most messages correctly, but there is one set, most ciphertext correctly, there is one ciphertext which doesn't take credit cookie, right? Because and that's not something you can check. You can check validity. So presumably the way to check validity is to encrypt many ciphertexts, try decrypting them, and you check their check the encrypts parameters, right?
Sure. So. But that is actually, this would mean essentially that for certain values you may not actually be able to complete the output of the function, right? So
you're implicitly saying that this function, because this function is total?
Is that because you're saying it's true that maybe once you're saying that one ciphertext that's
so C0 is something that the adversary publishes, right?
Yes.
So he publishes this, then the X is also presumably adversary chosen, right? The challenge.
Yes, but it depends because when the pseudo-random property that you require, then C is not adversarially chosen. C is honestly chosen.
Always.
And I always get blinded when I get to the middle. So, what about like actual instantiations of this scheme? So I will very briefly talk about this like generic construction. You can imagine that we can actually construct these things if we accept a weaker definition of VRF, which we call like bounded VRF. Imagine that VRF that it remains the pseudo-random property is only guaranteed as long as the number of queries at most a certain value, certain bound. And if we accept that, we can actually build this type of IBCAM using like cover-free families. So in principle, you imagine a cover-free family, we have a ensemble of we have a family of subsets over one QID. And then we say that F is actually Q cover-free if for each Fi in this family. And then if you consider for each S, that is the union of other Fi's, but other than the challenge one, this Fi, so let's see. S is the union of Fj, at most Q sets Fj, where Fj is chosen from the set F, except for that does not include the Fi. Then S does not cover Fi. So that's, and in addition to that, we have the property that we say that F is uniform if all of the subsets in F have the same size. So this is, we actually know such constructions of, and we know how to construct such families, and actually there is a deterministic polynomial time algorithm that actually given S and Q can return such an L uniform Q cover-free family over this 1 over ID, where the set F is actually of size at most S. We have S elements in the family. And we denote just like this algorithm that actually generates these values as S. So by doing that, we can actually like build a IBCAM scheme out of a standard CAM. by using this family is where we choose, we generate D secret keys, and D pairs of secret key and public keys, and then the master secret key becomes all of the secrets, and then the public key becomes all of the public keys. The master public key becomes all of the public keys. And the key derivation is very simple. We simply give the subset of keys that corresponds to the identity. So we first map the identity using S to the particular set, F of ID, and then we give those keys to that user. Or here we're talking about ID cams. And the encapsulation works in the standard way. We always do this mapping between ID and F of ID. And then we encapsulate for each, we generate a key for every public key in this set. And then the key for this identity, the actual key will become the XOR of all of the keys. And the ciphertext, all of the ciphertext. And the encapsulation is, we do the construction. We complete F of ID again. We complete the encapsulation of each CI using SKI, and we complete the key back. So this is a very simple construction. And what is interesting is that then if we define a similar property for CAM schemes as the pseudo-random property that we define for ID CAM, then we actually can have a VRF based on a simple assumption. That is a bounded VRF. So, here is just the CAM, and here is just it's a similar definition of security. So, like in the IBE case. But here we give this, the IBE case, you could query anything, get the secret key for any identity other than the challenge. And here is similar, except that the challenge identity, the challenge public key is PK1. So for PK0, we give the secret key.
What is PLD?
Pseudo-randomness is what the acronym that we use for that. Sorry for the name because it's actually not important. It's just saying it's pseudo-random security, pseudo-random decapsulation property for a CAM scheme. So we can define, and then we can actually show that like most existing schemes satisfy this property. So Algamo, we can very easily show. Sorry, here something happened to. This was not there, but you can actually have the Algamo encryption scheme or the CAM, not the summary Algamo, but just the CAM, and you can actually prove that this property follows from DDH. And likewise for you were saying like the pseudo-random property that we define, we can actually show like Rene Franklin IBE scheme, this is the definition. So actually the CAM is just is actually a bit simpler, and we can actually show that the same proof follows. And actually it's kind of expected that it follows from the proof follows from the same assumption as the INCPA assumption, because if you look at the ciphertext for the CAM, is actually independent of the identity. So as long as we chose ID0 to be ID star, and then the proof follows. So
you're saying that like the property is you can create a ciphertext without knowing what the identity is?
Yeah, it's oblivious. So yeah, in this case, it's actually maybe the definition could have been, it can be improved even to make as if you can generate a ciphertext obliviously. That's all we need for the transformation, actually. We don't need to choose a particular identity, because the identity that we choose is not important. So as long as we can generate the ciphertext obliviously, it's fine for the transformation.
So you're saying that maybe you could have a different definition of an ID, which says that you can create a media ciphertext, and maybe that suffices for...
That suffices for the transformation, yeah. Because we don't, nowhere we actually define the ID 0, like we just get an arbitrary one, whatever makes it more efficient. Scheme.
So that's a very natural property, right? So if you do that, if that works, then you're changing the definition and functionality of the ID, but you don't have to change you don't have to define a new notion of security, right? Because that follows, so you can...
Yes and no, because even though you can generate implicitly a ciphertext for a given identity, you may be able to test which identity it is. Maybe we don't know the randomness associated, so you may not have any idea what the key, like it's about the key, but you may have an idea about the identity. So in this case, you don't have any idea, but in some cases, you may actually have an idea what the identity is, but not about what the key is. Generate obliviously. But the thing is that you can actually prove that this thing is satisfied the pseudo-random property, and the proof follows exactly the proof of ECP of the Bonnet-Franklin IB. And like here is just a way of showing that. So like the public key choose one of the values here to be the public key. Then when you simulate the random oracle, you set the challenge to be G to the C, and for any other identity, you will simulate the random oracle knowing their R. So because you know the R, you can derive answer key derivation queries for any identity other than the challenge identity. Because you know R, and you can use G to the A, like which is the public key. And then once the ciphertext C star will be simply the other value here, and the key is set to be a Z. And here we can easily see that if Z equals EGG to the ABC, then K star will be the decryption of SK of C star using the secret key for the ID that we don't know. We actually don't know what that secret key is, but because it's G to the C, it would be G to the CA. But the key would have the right format, and if Z is random, so is the key. So we can do similar proof for the Waters IB chem. So it shows that essentially most of the CPA schemes do meet this notion. So this proof and that scheme, and then there is the Sakai-Kasai scheme. That is actually, as here, this scheme is quite simple, as we said, and the encryption. You just pick a T at random, and the ciphertext is EGD to the T, and the ciphertext N times T. So the encapsulation scheme is actually just ignores this part here. So the ciphertext, it becomes just G to the T. This part becomes the ciphertext of the chem, and T becomes the key of the chem. So sorry for not writing down the chem scheme of the Sakai-Kasai. But so if you actually apply this scheme to the R transformation, you actually get exactly the Dodizian-Polsky, except that T will have a very particular format. It's a particular value, so that's why the proof of Dodizian-Polsky doesn't follow from ours. And to prove that that particular value of T is fine, you have to to prove it separately. And we actually, the Bertuzzi-Polsky was nice to see that, the Sakaikas scheme was nice to see that it implies the Bertuzzi-Polsky, but it didn't buy us anything so far. So far we only know how to build things that we knew how to build before. And more recently, together with Catalano and Fieri, we actually get a different construction. So though I didn't formally introduce here, this is not really a standard IBCAM scheme, because in order to encrypt for a given identity, we need this value OXID. Here, which you need to know the master secret to compute that value. But in our transformation, that is not a problem, because when we generate the secret key, we actually know the master secret. Whereas when we generate the ciphertext, we know the master secret. But the transformation is actually pretty close to what Lizinskaya scheme did. The idea is that you get n pairs of values. So here we call alpha I and beta I. Beta for the 1 values and alpha I for the 0 values. And in addition to that, we got that this value is g to the a and g. And the key derivation, here is where we see that it's pretty similar to what Lizinskaya scheme is, because this is actually Lizinskaya unique signature scheme. So in order to do that, essentially we compute HI. Here is just a simple way of saying either we choose the left value or the right value depending on if IDI is 0 or 1. Because IDI is always a bit. So if IDI is 1, we compute HI as HI minus 1 to the power alpha I. Otherwise we use beta I. And in the secret, so we compute this value OXID, which is Lizinskaya. It has the same format as Lizinskaya unique signature scheme. And the secret key is actually HL to the power A, where A is the value that we had. The encapsulation has a very simple form. We just pick this last value, HL. So we compute this thing using the master secret or the OXID. And we compute the key as G1 HL to the T. And the ciphertext is G to the T. So the ciphertext is pretty common, and we actually don't need to, we can generate that ciphertext without knowing which identity so for there's another case where we don't care about the identity. And the encapsulation works as normal. We first check that this is correct, the OXID, and then we decrypt using SKID. And the proof is actually, so even though we use Lizinskaya scheme, actually we use a much simpler assumption, which is much simpler is relative here. It's still, it's not like BDH, but it's still a Q-type assumption. But it's non-interactive, unlike the original assumption, which you had to provide oracles that would reply to every index. So here we get G to the B, G to the like Q powers of B, G to the C and G. And we have to check whether T is actually EGG, C times B, Q plus 1. And actually this assumption we didn't introduce, it was already used before to prove selective security of IBE schemes. And we actually, in this case, our proof, again we guess the challenge identity, which means essentially we can only prove selective security. But if we actually consider selective security, this proof actually works for large domains. like the original Dodges and Polsky scheme. So, and the idea is the usual one. We're going to set up the public key so that we can answer key codes for ID different than ID star, and we're going to embed the challenge T into the challenge for the adversary, and then use that adversary to distinguish T from random. So how do we do this? The key generation. So again, we guess the challenge star identity, ID star. Now we set up the public key. The idea is actually quite simple. Like imagine that we guess the challenge identity to be 10011. We simply, for all these positions here, we're going to put B inside where B is G to the B, so just the first term. We're going to put B inside these values, and all of the other public key values, we're going to generate knowing the discrete log. And to make sure that the key has the right form, we still will use B, but we also randomize it. So implicitly what this is saying, like, is the secret key for positions where ID star matches ID matches ID star, the key will be B times beta I. Like if if an identity ID matches the identity ID star to position I, then we know that the public key was generated with B, and the corresponding secret key for that position would be either B times alpha I or B times beta I. And C will generate as the challenge ciphertext will generate as G to the C. And the first term, the G1, will also include B inside. And what is the idea of doing that? So imagine that we receive a query which is for ID different than ID star. So we know that at least because it's different from ID star, there will be one position where the two will differ. So because of that, we actually define this function here, alpha I, IDI, beta I, ID1 minus IDI. It's actually not too hard to see that, suppose that MJ, like if we consider the identity ID and ID star, if you truncate that identity at position J, what is the number of elements that they have in common? So that is what is MJ. So, and since we're considering inputs of size L, NL means that is the number of bits in common between ID and ID star. And because we consider ID different than ID star, NL is definitely less than L. So we can actually see that aux ID for a given identity can be computed as B raised to this power WID, which we can easily compute because we know all these values. And we can actually compute this because NJ for any identity, for any value here, NJ is less than L. And BN are the inputs that we received from the, so here is BQ, so B1, B2, BQ is the G raised to the BQ. So we have, we know all the values B1 to BL to BQ, but we don't know BQ plus 1, for instance. So but by using this knowledge, and why do we care about the number of positions in common? It's because exactly whenever they match something, the way we chose the public key, every time we match, the ID matches ID star, we're going to include one B element in the computation of age, of the element age. Sorry for the details. But essentially, we can compute the secret key, and we can, all the elements here, and we can also compute SKID, because SKID is HL raised to the power AB, because we computed G1 is B to the A, so this is G raised to little b times A. So essentially this means that this will come out, turns out to be B and L plus 1. And since ML is less than L, we know how to compute, ML is less than L, which L here is equals to Q. We know how to compute all of these elements. So we can compute everything here. And the challenge is actually quite simple. We define the same way WID star for this challenge. And actually now the value is corresponding to ID star. We don't need to consider ML. ML equals MJ equals to J for ID star. So that's why I didn't use MJ here, I just used J. Which means that we can compute all of these values because this is at most L, is exactly L, this element here. We can compute using BL. We cannot compute the secret key though, because the secret key contains the terms L plus 1 and L equals Q here. So we don't know how to compute that. So this is unknown to us. But we can compute still K star, the challenge that we're going to give to the adversaries using the input that we received, T. And it's easy to see that if T has this form, then K will be equals to the decapsulation. And if T is random, so is K. So you succeeded in that in the challenge. So now we're almost done. This part, I just wanted to mention some more recent results, but not details about these results. So first is that more recently, Hohenberger and Waters, they actually built a scheme for which you can prove the security, even for large inputs, like not selective security, because our scheme we can prove to be selective secure for large domains, but we didn't know how to prove it for large domains, for full security for large domains. And essentially, they showed such a scheme here, and the proof of security actually, so you see that there is some similarity between their scheme and ANA's and our scheme. And the proof of security uses a bit stronger assumption. It's the assumption where we give all the elements except we have a hole here in the middle, so we don't have the term G raised to the B to the L. And the goal here is to distinguish this element from random. And they prove this secure even for large domains. And more recently, Bonet, Montgomery, and Nathan, they proved, they modified Doddy's Yampolsky somehow. You can see this as a modification of Doddy's Yampolsky scheme, in which instead of just having one term S plus ID, as we had before, S plus X, in X before was an element in X in ZQ. Now we see X as a binary string, and we compute the proofs using these elements, the 1 over the product of these elements. But now to be able to verify is similar issue as the ANA's schemes, this is Sky's scheme, that in order to verify that, you have to verify that all of these elements, like you have to verify PR using PR minus 1, and then PR you verify the value. So you have to verify all these intermediate values that you receive. But interesting, like this scheme, like ours, they can prove secure, that is selective secure for large domains. But they also show how they will prove it fully secure for large domains and using what is known as admissible hash functions primitive. And this was introduced by Brian in 05, actually to transform implicitly a selective secure IB into a full secure. They used a similar property here. And in fact, we can actually show that, like, if we consider our scheme, this the IB cam that represented, that was used to build the VRF, you actually, by using the same proof as Waters and Hohenberger and Waters, using this same proof, we can actually prove our scheme secure, fully secure, under the same assumption, actually, the LBDDH assumption that they use in their proof. So you can actually consider that scheme as like giving a full proof of security for our scheme, plus they actually simplify the scheme a bit. Because instead of having 2 n pairs, they have n plus 1. So, and actually, but if we want to prove, we can also prove this our scheme. If we also use admissible hash functions, we can actually prove our scheme fully secure under the same assumption that we had before, plus the admissible hash functions. So, just to conclude, we presented here like some instantiations of our IBE suitable VRF suitable IBEs. It would be interesting if we could find all the instantiations. Actually, by looking at the Bonnier's more recent scheme or Hohenberg and Waters scheme, we can actually define similar IBEs implicitly, but it doesn't make sense to define an IBE for which you already know that they will give a VRF. But it would be interesting to find new ones. And more importantly, it would be like the schemes are still not very efficient. And even more importantly, the secure assumptions that were used so far, we only know how to prove full security based on Q-type assumptions. And it would be interesting if we could prove, like, use linear assumption or the bilinear Diffie-Hellman assumption. That remains still a big open problem, and would be extremely nice if we could obtain such a construction. So that concludes my talk.